The ratio test. The ratio test asks us to look at the limit of the ratio of subsequent terms. Well, here's a precise statement. So the question is whether the sum n goes from 1 to infinity of a sub n converges or diverges. I'm going to want to assume that all of the terms that I'm adding up, all of the a sub n's, are positive in order that I can use the comparison tests. I'll compute the limit of the ratio of subsequent terms. So I'm setting big L to be the limit as n approaches infinity of a sub n plus 1 over a sub n. And then there's three possibilities. Maybe that limit, maybe big L, is less than 1. And in that case, the ratio test says that the series converges. Maybe that limit is bigger than 1, in which case the ratio test says that the series diverges. And maybe that limit is equal to 1, in which case the limit test is simply silent. It might converge, it might diverge, we just don't know. The ratio test doesn't tell us any information when L is equal to 1. Why does this work? Well, what if the limit is less than 1? So I'm trying to figure out what happens when big L is less than 1. I want to show the series in that case converges. Well, if big L is less than 1, I can pick some very tiny value of epsilon so that even big L plus epsilon is less than 1. Then I can use epsilon in the definition of limit. So there must be some big N so that whenever little n is at least big N, the thing I'm taking the limit of, a sub n plus 1 over a sub n, must be within epsilon of L. So in particular, a sub n plus 1 over a sub n must be less than L plus epsilon. Now, how is this fact helpful? Well, I'm trying to calculate this series. I'm trying to sum a sub n goes from 1 to infinity. But I can break it up into two pieces when n is smaller than big N and when n is bigger than big N. Well, here's the piece when n is smaller than big N. It's just the sum of a finite sum. I'm not going to have any trouble adding those numbers up. But then I've got the rest of the series that I have to add up. Right? I have to add up a sub big N plus a sub big N plus 1 and so on. And this is the hard part, right? Because I've got dot, dot, dot forever. But what I know now is that I can control the ratio between subsequent terms, maybe not here, but at least here. Right? I know that a sub big N plus 1 is less than r times a sub big N. And I know that a sub big N plus 2 is less than r times a sub big N plus 1, which itself is less than r times a sub big N. So all of that is to say that this thing here is, well, not equal to this, but this is an overestimate of what was there before. So now I've got that this series is at least less than this first part plus the rest. But what do I know about the rest? Well, the rest of this thing is now a geometric series, and I know that this geometric series converges because little r is less than 1. So I can replace that with this convergent geometric series. And in light of this, right, this is really now setting up a comparison test. I'm really saying that the sequence of partial sums is bounded by this. And since the sequence of partial sums is monotone, because all of the terms that I'm adding up are positive, I then know that this series converges. And what if the limit is bigger than 1? So I'm trying to figure out what happens when big L is at least 1. And I want to show that in that case, the series diverges. Well, if big L is bigger than 1, then I can choose some tiny epsilon so that big L minus epsilon is also bigger than 1. And then I can use that epsilon in the definition of limit. So there's some big N so that whenever little n is bigger than or equal to big N, this ratio, the thing I'm taking the limit of, is within epsilon of the limit L. So in particular, this ratio is bigger than big L minus epsilon. Now, why is that significant? What I'm trying to calculate is this series, or I'm at least trying to figure out if it converges or diverges. And I could start just adding up terms, right? A sub 1 plus a sub 2, eventually I get to a sub big N minus 1, then a sub big N plus a sub big N plus 1, and so on. I keep on adding up terms, taking a limit of partial sums, strictly speaking. But I know that all of these terms are positive. So if I throw away a bunch of terms, well, this isn't equal to this anymore, but this is now larger than this thing where I've thrown away a whole bunch of terms. I'm just going to start with the a sub big N term. Now, what else do I know? Because a sub little n plus 1 over a sub n is bigger than this whenever little n is bigger than or equal to big N, I can underestimate this. Right? This is saying that a sub big N plus 1 is larger than r times a sub big N, telling me that this is bigger than r times this, which is also bigger than r times this, which means this is larger than r squared times this. This term here, a sub big N plus 3, is larger than r cubed times this. What I'm really saying is that this infinite series is at least this infinite series. But what kind of infinite series is this? Well, this is just a geometric series, right? That's the geometric series, the sum k goes from 0 to infinity of r to the k times a sub big N. And what do I know about that infinite series? That infinite series diverges, right? I can make the partial sums for this as large as I'd like, as long as I go far enough out in the sequence. Well, that means that this series also diverges. And what does the ratio test say if the limit is equal to 1? When L is equal to 1, the series might converge or it might diverge. The ratio test is just silent in that case. It doesn't tell us any information. And why not? Well, when L was less than 1, then I could pick a value of epsilon so small that even L plus epsilon was less than 1. And when L was bigger than 1, I could pick a value of epsilon so small that even big L minus epsilon was bigger than 1. But when L is equal to 1, there's no hope for me being able to choose a small enough epsilon so that I can control the ratio between subsequent terms to eventually all be less than 1 or eventually all be bigger than 1. So I'm not going to succeed in comparing my series to a geometric series. So that's the ratio test. But finally, a warning. The ratio test tells us to compute this, the limit of the ratio between subsequent terms. It's important to emphasize that that limit is not calculating this. What the ratio test is telling us is not the value of this series. What the ratio test is providing information about is whether or not this series converges or diverges. That's what this big L is helping us find.